Hello, everybody, and welcome to the lecture for Tuesday of week 14. So just a reminder, this is our last week of lectures, and the homeworks and quizzes are optional this week, and you'll get bonus points for them. Okay, so the topic today is elliptic curves. And so what are elliptic curves? Well, we've spent a lot of time in this class talking about degree 2 or quadratic equations, in particular about how they behave when we look at solutions like in the integers or mod p, and what kinds of things we can say about that. We've noticed some really interesting structure, given some interesting applications, for example, to Mersenne primes, like the Lucas-Lemma test. Okay, but we've spent a lot of time now with the degree 2 equations, and I feel like we've understood quite a bit. The next natural thing to do is to ask, sort of, what about degree 3 equations? So an equation where some variable appears to a third power. And so this is the subject of elliptic curves. In particular, sort of when we're talking about elliptic curves, usually we reduce to the following special type of equation. We look at an equation of the form y squared is equal to x cubed plus, y squared is equal to some degree 3 polynomial on x. You can sort of make some changes of variables to reduce lots of degree 3 equations to this. So one example is the equation y squared is equal to x cubed plus 8. So if we just look at the solutions in R2, so the solutions where x and y are real numbers, well, we just get this sort of fun looking curve over here. And well, it turns out there are some amazing things about elliptic curves, this one in particular, but in sort of all elliptic curves, so all sort of solutions to degree 3 equations. Most of these amazing things sort of boil down to the following statement, which is the points on this curve, well, with a minor modification, they actually form a group. So there's some way to sort of take 2 points on this curve and add them together to get a new point. So it turns out if I add this point and this point, I will get this point. Okay, and so having this group structure is going to be a very powerful thing that lets you do a lot of interesting things with elliptic curves. And we're just going to, this week, we're just going to sort of scratch the very tip of that iceberg. But I'll tell you about some interesting things. One point I want to make is, like, we've actually seen this kind of phenomenon before, where you sort of have some geometric object and it's sort of like an equation, and sort of you look at this graph and sort of the solutions to that equation of this graph, like the points on it form a group. So one simple example is if you look at x squared plus y squared is equal to 1. So for example, this showed up when we were studying the Gaussian integers, but more generally shows up when you study the complex numbers. This is just saying the absolute value of a complex number is equal to 1 if you take their complex number to be x plus yi. And if you think of it like that, you see these are real solutions, x squared plus y squared equals 1. So this circle, they form a group by thinking of them as being the complex numbers. So this is another situation where you have sort of this geometric object, a circle, that really sort of forms a group. So you can multiply any 2 of these by treating them as complex numbers, and you'll land somewhere back on this shape. Okay. More generally, if you sort of fix any positive integer or even real number d, the solutions to x squared plus dy squared will be, or sorry, not positive, positive or negative integers. So if you fix any integer or sort of any real number d, then the solutions to x squared plus dy squared equals 1, these will also form a group. So this is something we looked at just for the integer solutions, but it turns out sort of the same argument works for like the real number solutions, x and y. We studied this sort of just by working in the quadratic integers z squared of d, and then this was the equation saying the norm was equal to 1, and because the norm is multiplicative, so you can see that this forms a subgroup. Like if you multiply together 2 of these things, 2 solutions, sort of using the multiplication law in z squared of d, then you get a new solution. And so this is what we sort of, this was the structure we used when we were studying Pell's equation. And for example, like when we were like trying to use it to compute square triangular numbers and things like this. Okay. So this is sort of not a completely foreign idea that sort of some geometric object could actually give you like the points on it could be a group. But here it's going to happen in sort of a more complicated way, and maybe a more interesting way. So let me just describe how you add 2 points. I mean, so to say, if I'm saying this is a group, I have to tell you how to add 2 points. Okay, and so basically it works like this. Say I have some point P and Q, and I want to compute, so I have 2 points P and Q, and I want to compute P plus Q. So I'm going to sort of start with P and Q, and then I just draw the line between them. And it turns out that, well, except for one exception I'll talk about in a second, when you draw this line, there's going to be exactly one other point where it intersects this elliptic curve. So here, if I draw the line between P and Q, then it intersects with this third point R. And then you don't take that point R to be P plus Q. Instead, you sort of flip about the x-axis to get P plus Q. So you sort of take the intersection, the third intersection point, and then you flip it about the x-axis. So sort of here, sort of we're using the fact that like, so note that if x, y is a solution, so is x minus y. And that's because the only place that y shows up is sort of as y squared. So this minus sign goes away. So if you just look at this equation we're looking at, y squared is equal to x cubed plus 8. So if I plug in minus y, I get the same thing as I do when I get y. Okay, so and this is a little bit funny, but it works. And we're going to sort of talk about this a lot in class on Tuesday. So we'll sort of explore how this process works and how you can actually sort of compute with this process. But let me sort of point out before that what the problems are. So again, so our algorithm was if we want to compute P plus Q, we draw the line through P and Q. We take its third point of intersection with E, and then we reflect it across the x-axis to get P plus Q. So what are these 2 issues? Well, I said we're going to take the third point of intersection of this line with our curve. But what if there aren't 3 points of intersection? So in class, we'll explain why there are always sort of at most 3 points. But you can sort of just write down some examples where you could sort of see that there aren't 3 points. So if I take P and Q to lie on sort of to have the same x coordinate, so they're lying on this vertical line, and I draw it between them, like this vertical line doesn't intersect this curve anywhere else. So that's one problem. And then the other problem is sort of what if P is equal to Q? Then sort of what does it mean to draw the line? I mean, there's lots of lines through P and Q are the same point. So we have to sort of tackle both of these issues. Let's do the what if P and Q have the same x coordinate first. Well, to do this, we're just going to add one more point. Which we call infinity. And so some of the idea is, what does this point correspond to? This corresponds to the vertical asymptote. So there's sort of ways to make this more precise, but let me just sort of say it like that. So if I look at this graph, the vertical asymptote of the graph. So if I look at this graph, like sort of as I sort of go, my x gets bigger and bigger, I'm sort of tilting off to infinity. I'm sort of tilting off sort of to infinity in the y coordinate sort of faster and faster. And really sort of you can sort of think about that as sort of having, well, it's not quite a vertical asymptote because like it doesn't ever line up against sort of a vertical line, but somehow like sort of this line is getting straighter and straighter, going straight up as it goes to infinity, as x goes to infinity. And so what we can think is, let's add a point that sort of we're sort of converging towards, and we'll sort of just treat it as being that sort of vertical line. And so really what I mean when I say sort of adding corresponding vertical asymptote of the graph, what I mean is sort of we're just adding a point that lies on every vertical line. So that fixes this problem, because now if I sort of take the third point of intersection, I get sort of infinity. So now sort of this is my third point of intersection. So it's sort of a funny thing. I'm just sort of declaring, let there be a new point added to this sort of to this graph, which sort of just lies on every vertical line. It's sort of a funny thing to do, but it's so there are various notions of geometry where this is actually a sort of natural operation. Like if you look into projective geometry, this is sort of what we're doing here. But I don't want to sort of spend time talking about that. So we're just going to throw in this extra point infinity that lies on every vertical line, and then we sort of have a third point of intersection. We should also sort of, okay, so like here, sort of I'm saying P plus Q. Okay, so now sort of if I try to add this P and Q, they're on the same x-axis, same x point, and I get this vertical line. And so this gives me sort of my R up here is infinity. And then I'm supposed to be able to flip infinity about the x-axis. And so that would sort of be like this minus infinity down here, but I'm not going to, somehow I'm going to say minus infinity is the same as infinity. So, so let me add sort of, when we flip infinity about the x-axis, we get infinity back. So P plus Q is equal to infinity if P and Q are as in the first picture. Many times sort of P and Q sort of both lie on the same vertical line, have the same x coordinate, but different y coordinates. These two or these two. So these are a bunch of different points you can add together and you get infinity. Okay. Good. So that sort of fixes, or at least tells us sort of how to extend this rule to this case where we don't have 3 intersection points. The other thing we had to do was sort of understand how to extend this rule when we don't have when P is equal to Q. So how do you sort of compute P plus P? Well, what we do actually is we just, somehow, if you think about it, if you took points closer to and closer to this, so you took sort of points that were nearby and you sort of drew the line between them, like as your points got closer and closer, those lines would sort of be approaching the tangent line to the graph at this point. And so that's what we do. We just take the tangent line. Okay, so we, in this case, we sort of take the tangent line. And again, so we can justify this more carefully with why this is a good idea. But I'm just sort of declaring it to be true. I'm just telling you that's the rule. That's the rule we use to sort of give this addition law for points on our curve. Okay, and that sort of solves the main issues. And sort of amazing fact, and sort of a lot of work to spell it out and sort of check all the details by sort of computing, but you can do it just by brute force computation. And this really gives you, a group law. Like, so okay, so to sort of check it, you'd have to sort of check not just any group law, sorry, a commutative group law. So you'd have to sort of check that like this satisfies like the associative rule for addition. You'd have to check everything has a negative. But in fact, that part's easy, checking everything as a negative because of what I've already said. Because the identity element is infinity. So identity element is infinity. And then sort of the negatives of something is just sort of something you add to it to get infinity. So like here, Q is negative P. So P minus Q is equal to infinity, which is sort of the identity element. So sort of the inverse here's the inverse of x, y is x minus y. And again, that's because sort of if infinity is the identity element, well, if I want to sort of add up two things to get infinity, I can just take sort of two things that lie on the same vertical line. That's sort of somehow that's how we sort of added this point to infinity anyway. So we had an answer when we added two things on a vertical line. So somehow really you can think what we were doing when we sort of added in this point infinity was we were sort of adding in an identity element. Okay. So that's an amazing thing. And so one of the things we're going to do on the worksheet on Tuesday is you're going to work out some sort of specific formulas for this group law. And well, we're going to work mostly sort of with this specific equation, but actually this works for any equation of the form y squared is equal to x cubed plus ax plus b, or even you can sort of be a little bit more general, as long as sort of this x cubed plus ax plus b has no multiple roots. And so sort of this sort of comes up. You need this to be true to sort of have a tangent line at every point. So that's sort of a fun calculus exercise to check why that's the case. But sort of somehow like this, if this equation had a multiple root, then this description we gave of the group law would break down exactly when we sort of talk about adding a point to itself, because we wouldn't be able to sort of take the tangent line. So something else amazing is, well, I was sort of looking at the picture of the real numbers. So I was sort of looking at real solutions to this equation. But really, this group law works for solutions sort of with entries in any field. So we'll see that basically when we, so we'll see that when we sort of work out the formulas for the group law. And we'll see, so those formulas, like if you sort of, some of you start with x and y coordinates in one field, like it spits out x and y coordinates in that same field. So that's okay. So those are sort of some more basic facts, some sort of deeper facts. What kind of things we like to do as number theorists? Like one thing we like to do is like look at integer solutions to equations. And so as a result of Siegel, it says if a and b are integers, then there are only finitely many integer solutions to this equation. So this is sort of a fun result. Just an example, if you write y squared is equal to x cubed plus 8, here are a few integer solutions. Plug these in and check they work. And maybe there are more, but if there are more, there are only finitely many. Good. Another fun fact is that if you sort of take this a and b to be rational numbers, so again, for example, you can look at y squared is equal to x cubed plus 8, then there are only finitely many, then there can be infinitely many rational solutions. So there sort of can be infinitely many x and y, where x and y are both rational numbers that give you a solution to this equation. But sort of because these group laws sort of work over any field, like those rational solutions will form a group. And if you look at that group, what happens is actually, even though there can be infinitely many solutions, they can always be generated from finitely many. So you can always start with some finite set of solutions and then generate all other solutions by adding together the points, which means sort of by computing these lines through 2 points and then sort of the intersection and flipping it and just iterating that process. So you can sort of find some finite set of points on this curve where every other rational point on this curve is gotten by using this group law. So this is called the Mordell-Weil theorem, and this is very an interesting and deep theorem. And this looks a lot like integer solutions to Pell's equation. So if you remember back to what we were doing the last couple of weeks, we're looking at like x squared minus dy squared is equal to 1. And then we sort of saw that we could take in one solution to that and then use sort of use the group structure of the norm and z squared of d to generate many new solutions. And then we sort of even talked about how you sort of actually, you could take one solution and generate all other solutions from it. And so sort of the Mordell-Weil theorem is something like that. It's sort of saying if I have sort of two rational solutions, or I can sort of generate all the rational solutions starting from some finite set of them just by sort of iterating this group law. So this, I mean, elliptic curves, like sort of, and they're very central objects in like modern research in number theory, actually, which I think is sort of fun to see that you can sort of, we're able to understand everything, like so many things about degree 2 equations. But sort of once you start talking about degree 3 equations, like you're talking about sort of modern research in number theory, like sort of the kind of stuff I do when I'm not teaching this class. So for example, Fermat's last theorem, so this is the sentence that there are no non-trivial integer solutions to the equation x to the n plus y to the n is equal to z to the n when the exponent n is greater than or equal to 3. So this was sort of conjectured by Fermat sort of many, many years ago, and so he famously claimed he had a proof, but couldn't fit it in the margins, which is sort of a great homework excuse. And well, he didn't have a proof, and it sort of took hundreds of years for someone to prove it. And it was actually relatively recently. So this result was established rigorously in the 90s by Andrew Wiles with sort of an important assistance by Richard Taylor. And so, well, so the result they proved doesn't look like it's about elliptic curves, but actually sort of somehow the way they proved Fermat's last theorem is by reducing sort of this statement about solutions to x to n plus y to z to n equals z to n to some problem about elliptic curves. And that problem ended up being a very hard problem about elliptic curves, but that's sort of the problem they actually solved. So they sort of did some rewriting to change this into a problem about elliptic curves and then solve that problem. Okay, so somehow elliptic curves sort of show up in sort of extremely modern research in number theory that sort of solves sort of ancient questions in number theory, which is sort of a sign of sort of a central and beautiful idea. One more fact, just for fun, is I mean, like when I say it's modern research, like it really is. I mean, so there's very important open problems about elliptic curves. So one good example is the Birch and Swinnerton-Dyer conjecture. So this is one of the 7 Clay Millennium problems. These are math problems with sort of $1 million prize for solving them, provided by the Clay Foundation. And so this is sort of, they're supposed to be sort of somehow like the most difficult, some of the most difficult problems, open problems in mathematics. And so the Birch and Swinnerton-Dyer conjecture is one of them. And very roughly, this is a conjecture about relating sort of rational and mod p solutions of the y squared is equal to x cubed plus ax plus b when a and b are integers. So somehow, if you think about elliptic curves hard enough, you can sort of come away with $1 million, maybe. Maybe lots of people have tried, so I wouldn't pin your retirement on it. Okay, but we're going to talk about sort of more sort of concrete applications of elliptic curves, especially to cryptography, on Thursday. And then Tuesday, we're going to just do some computations in class. So I will see you there.